Linear algebra is the branch of mathematics concerning vector spaces and linear mappings between such spaces. It includes the study of lines, planes, and subspaces, but is also concerned with properties common to all vector spaces. The set of points with coordinates that satisfy a linear equation forms a hyperplane in an n-dimensional space. The conditions under which a set of end hyperplanes intersect in a single point is an important focus of study in linear algebra. Such an investigation is initially motivated by a system of linear equations containing several unknowns. Such equations are naturally represented using the formalism of matrices and vectors. Linear algebra is central to both pure and applied mathematics. For instance, abstract algebra arises by relaxing the axioms of a vector space, leading to a number of generalizations. Functional analysis studies the infinite-dimensional version of the theory of vector spaces. Combined with calculus, linear algebra facilitates the solution of linear systems of differential equations. Techniques from linear algebra are also used in analytic geometry, engineering, physics, natural sciences, computer science, computer animation, and the social sciences. Because linear algebra is such a well-developed theory, nonlinear mathematical models are sometimes approximated by linear models. History. The study of linear algebra first emerged from the study of determinants, which were used to solve systems of linear equations. Determinants were used by Leibniz in 1693, and subsequently, Gabriel Cramer devised Cramer's rule for solving linear systems in 1750. Later, Gauss further developed the theory of solving linear systems by using Gaussian elimination, which was initially listed as an advancement in geodesy. The study of matrix algebra first emerged in England in the mid-1800s. In 1844, Hermann Grassmann published his theory of extension, which included foundational new topics of what is today called linear algebra. In 1848, James Joseph Sylvester introduced the term matrix, which is Latin for womb. While studying compositions of linear transformations, Arthur Cayley was led to define matrix multiplication and inverses. Crucially, Cayley used a single letter to denote a matrix, thus treating a matrix as an aggregate object. He also realized the connection between matrices and determinants, and wrote, "There would be many things to say about this theory of matrices which should, it seems to me, precede the theory of determinants." In 1882, Huzia Tevfik Pasha wrote the book titled Linear Algebra. The first modern and more precise definition of a vector space was introduced by Peano in 1888. By 1900, a theory of linear transformations of finite-dimensional vector spaces had emerged. Linear algebra first took its modern form in the first half of the 20th century, when many ideas and methods of previous centuries were generalized as abstract algebra. The use of matrices in quantum mechanics, special relativity, and statistics helped spread the subject of linear algebra beyond pure mathematics. The development of computers led to increased research in efficient algorithms for Gaussian elimination and matrix decompositions, and linear algebra became an essential tool for modeling and simulations. The origin of many of these ideas is discussed in the articles on determinants and Gaussian elimination. Educational history. Linear algebra first appeared in graduate textbooks in the 1940s and in undergraduate textbooks in the 1950s. Following work by the School Mathematics Study Group, U.S. high schools asked 12th grade students to do matrix algebra, formerly reserved for college, in the 1960s. In France during the 1960s, educators attempted to teach linear algebra through affine-dimensional vector spaces in the first year of secondary school. This was met with a backlash in the 1980s that removed linear algebra from the curriculum. In 1993, the US-based Linear Algebra Curriculum Study Group recommended that undergraduate linear algebra courses be given in application-based matrix orientation, as opposed to a theoretical orientation. Scope of study. Vector spaces. The main structures of linear algebra are vector spaces. A vector space over a field F is a set V together with two binary operations. Elements of I are called vectors and elements of F are called scalars. The first operation, vector addition, takes any two vectors v and w and outputs of third vector v plus w. The second operation, scalar multiplication, takes any scalar and any vector v and outputs a new vector av. The operations of addition and multiplication in a vector space must satisfy the following axioms. In the list below, let u, v and w be arbitrary vectors in V, and a and b scalars in F. The first four axioms are those of E being an abelian group under vector addition. Vector spaces may be diverse in nature, for example, containing functions, polynomials or matrices. Linear algebra is concerned with properties common to all vector spaces. Linear transformations, similarly as in the theory of other algebraic structures. Linear algebra studies mappings between vector spaces that preserve the vector space structure. Given two vector spaces V and W over a field F, a linear transformation is a map that is compatible with addition and scalar multiplication. For any vectors u, v, v and a scalar f. Additionally, for any vectors u, v, v and scalars a, b, f. When a bijective linear mapping exists between two vector spaces, we say that the two spaces are isomorphic. Because an isomorphism preserves linear structure, two isomorphic vector spaces are essentially the same from the linear algebra point of view. One essential question in linear algebra is whether a mapping is an isomorphism or not, and this question can be answered by checking if the determinant is non-zero. If a mapping is not an isomorphism, linear algebra is interested in finding its range in the set of elements that get mapped to zero, called the kernel of the mapping. Linear transformations have geometric significance. For example, 2 times 2 real matrices denote standard planar mappings that preserve the origin, subspaces, span, and basis again. In analog with theories of other algebraic objects, linear algebra is interested in subsets of vector spaces that are themselves vector spaces. These subsets are called linear subspaces. For example, both the range and kernel of a linear mapping are subspaces, and are thus often called the range space and the null space. These are important examples of subspaces. Another important way of forming a subspace is to take a linear combination of a set of vectors v1, v2, vk, where a1, a2 are scalars. The set of all linear combinations of vectors v1, v2, vk is called their span, which forms a subspace. A linear combination of any system of vectors with all zero coefficients is the zero vector of V. If this is the only way to express the zero vector as a linear combination of v1, v2, vk, then these vectors are linearly independent. Given a set of vectors that span a space, if any vector w is a linear combination of other vectors, then the span would remain the same if we removed w from the set. Thus, a set of linearly dependent vectors is redundant in the sense that there will be a linearly independent subset which will span the same subspace. Therefore, we are mostly interested in a linearly independent set of vectors that spans a vector space V, which we call a basis of E. Any set of vectors that spans V contains a basis, and any linearly independent set of vectors in V can be extended to a basis. It turns out that if we accept the axiom of choice, every vector space has a basis. Nevertheless, this basis may be unnatural, and indeed, may not even be constructible. Any two bases of a vector space V have the same cardinality, which is called the dimension of E. The dimension of a vector space is well defined by the dimension theorem for vector spaces. If a basis of V has finite number of elements, V is called a finite dimensional vector space. If V is finite-dimensional and U is a subspace of V, then dim U dim V. If U1 and U2 are subspaces of V, then one often restricts consideration to finite-dimensional vector spaces. A fundamental theorem of linear algebra states that all vector spaces of the same dimension are isomorphic, giving an easy way of characterizing isomorphism. Matrix theory: a particular basis, V1, V2, Vn, of V allows one to construct a coordinate system in V. The vector with coordinates is the linear combination. The condition that V1, V2, Vn span V guarantees that each vector V can be assigned coordinates, whereas the linear independence of V1, V2, Vn assures that these coordinates are unique. In this way, once a basis of a vector space V over F has been chosen, V may be identified with the coordinate n space Fn. Under this identification, addition and scalar multiplication of vectors in V correspond to addition and scalar multiplication of their coordinate vectors in Fn. Furthermore, if V and W are an n-dimensional and m-dimensional vector space over F, and a basis of V and a basis of W have been fixed, then any linear transformation T, VW may be encoded by an M times n matrix A with entries in the field F, called the matrix of T with respect to these bases. Two matrices that encode the same linear transformation in different bases are called similar. Matrix theory replaces the study of linear transformations, which were defined axiomatically, by the study of matrices, which are concrete objects. This major technique distinguishes linear algebra from theories of other algebraic structures, which usually cannot be parameterized so concretely. There is an important distinction between the coordinate n space Rn and a general finite-dimensional vector space V. One major application of the matrix theory is calculation of determinants, a central concept in linear algebra. While determinants could be defined in a basis-free manner, they are usually introduced via a specific representation of the mapping. The value of the determinant does not depend on the specific basis. It turns out that a mapping has an inverse if and only if the determinant has an inverse. If the determinant is 0, then the null space is non-trivial. Determinants have other applications, including a systematic way of seeing if a set of vectors is linearly independent. Determinants could also be used to solve systems of linear equations, but in real applications, Gaussian elimination is a faster method. Eigenvalues and eigenvectors in general. The action of a linear transformation may be quite complex. Attention to low-dimensional examples gives an indication of the variety of their types. One strategy for a general n-dimensional transformation T is to find characteristic lines that are invariant sets under T. If V is a non-zero vector such that TV is a scalar multiple of V, then the line through 0 and V is an invariant set under T and V is called a characteristic vector or eigenvector. The scalar lambda such that TV equals lambda V is called a characteristic value or eigenvalue of T. To find an eigenvector or an eigenvalue, we note that where I is the identity matrix, for there to be non-trivial solutions to that equation, det equals 0, the determinant is a polynomial, and so the eigenvalues are not guaranteed to exist if the field is R. Thus, we often work with an algebraically closed field such as the complex numbers when dealing with eigenvectors and eigenvalues so that an eigenvalue will always exist. It would be particularly nice if given a transformation T taking a vector space V into itself we can find a basis for V consisting of eigenvectors. If such a basis exists, we can easily compute the action of the transformation on any vector. If V1, V2, Vn are linearly independent eigenvectors of a mapping of n-dimensional spaces T with eigenvalues lambda1, lambda2, lambda(n), and if V equals A1 V1 plus and Vn, then such a transformation is called a diagonalizable matrix, since in the eigenbasis, the transformation is represented by a diagonal matrix. Because operations like matrix multiplication, matrix inversion, and determinant calculation are simple on diagonal matrices, computations involving matrices are much simpler if we can bring the matrix to a diagonal form. Not all matrices are diagonalizable. Inner product spaces. Besides these basic concepts, linear algebra also studies vector spaces with additional structure, such as an inner product. The inner product is an example of a bilinear form, and it gives the vector space a geometric structure by allowing for the definition of length and angles. Formally, an inner product is a map that satisfies the following three axioms for all vectors u, v, w in V and all scalars are in F. Conjugate symmetry. Note that in R, it is symmetric. Linearity in the first argument. Positive definiteness. With equality only for v equals 0. We can define the length of a vector v in V by and we can prove the Cauchy-Schwarz inequality. In particular, the quantity, and so we can call this quantity the cosine of the angle between the two vectors. Two vectors are orthogonal if an orthonormal basis is a basis where all basis vectors have length 1 and are orthogonal to each other. Given any finite-dimensional vector space, an orthonormal basis could be found by the Gram-Schmidt procedure. Orthonormal bases are particularly nice to deal with, since if V equals A1 V1 plus and Vn, then the inner product facilitates the construction of many useful concepts. For instance, given a transform T, we can define its Hermitian conjugate T** as the linear transform satisfying if T satisfies T. T** equals T** T. We call T normal. It turns out that normal matrices are precisely the matrices that have an orthonormal system of eigenvectors that span V. Some main useful theorems. A matrix is invertible, or non-singular, if and only if the linear map represented by the matrix is an isomorphism. Any vector space over a field F of dimension n is isomorphic to Fn as a vector space over F. Corollary. Any two vector spaces over F of the same finite dimension are isomorphic to each other. A linear map is an isomorphism if and only if the determinant is non-zero. Applications. Because of the ubiquity of vector spaces, linear algebra is used in many fields of mathematics, natural sciences, computer science, and social science. Below are just some examples of applications of linear algebra. Solution of linear systems. Linear algebra provides the formal setting for the linear combination of equations used in the Gaussian method. Suppose the goal is to find and describe the solution, if any, of the following system of linear equations. The Gaussian elimination algorithm is as follows. Eliminate x from all equations below L1, and then eliminate y from all equations below L2. This will put the system into triangular form. Then, using back substitution, each unknown can be solved for. In the example, x is eliminated from L2 by adding L1 to L2. X is then eliminated from L3 by adding L1 to L3. Formally, the result is, now y is eliminated from L3 by adding minus 4L2 to L3. The result is, this result is a system of linear equations in triangular form, and so the first part of the algorithm is complete. The last part, back substitution, consists of solving for the known in reverse order. It can thus be seen that then, z can be substituted into L2, which can then be solved to obtain next, z, and y can be substituted into L1, which can be solved to obtain the system is solved. We can, in general, write any system of linear equations as a matrix equation. The solution of this system is characterized as follows. First, we find a particular solution x0 of this equation using Gaussian elimination. Then, we compute the solutions of x equals 0, that is, we find the null space n of A. The solution set of this equation is given by, if the number of variables is equal to the number of equations, then we can characterize when the system has a unique solution. Since n is trivial if and only if det A0, the equation has a unique solution if and only if det A0. Least squares best fit line. The least squares method is used to determine the best fit line for a set of data. This line will minimize the sum of the squares of the residuals. Fourier series expansion. Fourier series are a representation of a function f minus pi r as a trigonometric series. This series expansion is extremely useful in solving partial differential equations. In this article, we will not be concerned with convergence issues. It is nice to note that all Lipschitz continuous functions have a converging Fourier series expansion, and nice enough discontinuous functions have a Fourier series that converges to the function value at most points. The space of all functions that can be represented by a Fourier series form a vector space. Moreover, this space is also an inner product space. With the inner product, the functions gn equals sim for n greater than 0 and hn equals cos for n0 are an orthonormal basis for the space of Fourier expandable functions. We can thus use the tools of linear algebra to find the expansion of any function in this space in terms of these basis functions. For instance, to find the coefficient tak, we take the inner products with hk, and by orthonormality, that is, quantum mechanics. Quantum mechanics is highly inspired by notions in linear algebra. In quantum mechanics, the physical state of a particle is represented by a vector, and observables are represented by linear operators on the underlying vector space. More concretely, the wave function of a particle describes its physical state and lies in the vector space L2, and it evolves according to the Schrödinger equation. Energy is represented as the operator, where V is the potential energy. H is also known as the Hamiltonian operator. The eigenvalues of H represents the possible energies that can be observed. Given a particle in some state phi, we can expand phi into a linear combination of eigenstates of H. The component of H in each eigenstate determines the probability of measuring the corresponding eigenvalue, and the measurement forces the particle to assume that eigenstate.